How are you today? Today we are going to discuss on some common nucleophiles listed in increasing order of nucleophilicity in hydroxylic solvents such as water and alcohols. So we'll start discussing on this category of nucleophiles. These are strong nucleophiles, and you can see here most of these nucleophiles are negatively charged, but we also have some neutral nucleophiles in this category, and also you have also halide ions in this category, but not all, but iodide ions. And I will discuss this further, why not all of them are in that category. In this second category of nucleophiles, that's the moderate nucleophiles, you can see you have the bromide and the chloride as in this category, and you also have some neutral nucleophiles in this category. In the last category of that is a category of weak nucleophiles, we have fluoride ions, we also have water and methanol. These are just examples. These are not all the weak nucleophiles that we have. And I wanted to highlight the fact that you have this halide ion, that's a fluoride ion, and it's a weak nucleophile. And why is it a weak nucleophile? Because this is a very small ion, and the nucleus, which is positively charged, is strongly attracted to the outermost shell electrons, making them not available for bonding with other electron lacking species. So we are going to discuss on the trends in nucleophilicity. And number one, a species with a negative charge is a stronger nucleophile than a similar species without a negative charge. In particular, a base is a stronger nucleophile than its conjugate acid. So here we have bases and their conjugate acids. So hydroxyl ion is the base of the conjugate acid. In this case is water, and it's a stronger nucleophile as compared to the conjugate acid. So similarly, this is the base, this is the conjugate acid, and the base is a stronger nucleophile. And in the third example, this is a base and this is the conjugate acid, and the base is stronger as compared to the conjugate acid. Number two, nucleophilicity decreases from left to right in the periodic table following the increase in electronegativity from left to right. And that is because the more electronegative elements have more tightly held non-bonding electrons that are less reactive towards forming new bonds. Non-bonding electrons are those which are not involved in the formation of covalent bonds, but can be availed to other electron-lacking species, electrophilic species, to form new bonds. So when it comes to more electronegative atoms, they are mean with these electrons, so they don't easily share with those which are lacking in electrons. But the less electronegative atoms, when you're comparing the same the same column, not column, sorry, the same row in the periodic table, then it means that the ones which are less electronegative will always result into stronger nucleophiles as compared to the ones which are more electronegative. So in this case, these are the examples. Even this neutral molecule, this is less, nitrogen is less electronegative as compared to oxygen, and therefore leads to a stronger nucleophile molecule as compared to oxygen. Similarly, phosphorus is less nucleophilic, less electronegative, and therefore it results to a stronger nucleophile as compared to sulfur. Number three, nucleophilicity increases down the periodic table following the increase in size and polarizability, and also decrease in electronegativity. We've already highlighted in part two that decrease in electronegativity always leads to increase in nucleophilicity. So as you move down the column in the periodic table, as in group 7 of the periodic table, that's the halogens, you find that the nucleophilicity increases down the periodic table. So the fluoride is the smallest ion, followed by chloride, followed by bromide, and the largest is iodine. So as you increase the shells, as you move down the periodic table, of course you add an additional shell, and you also the ion becomes polarizable as compared to the ones which are the smaller ones, like the fluoride ions. So in this case, in this halogen series, iodide is the largest ion, and you find that this is very highly polarizable because it's very large. So the nucleus is far away from the outermost shell electrons, and therefore it's not able to attract those electrons strongly leading to the nucleus having some partial positive charge and the outermost shell having some partial negative charge. So that way, you find that that ion is polarizable. So the electrons on the outermost shell can easily be accessed by any electron lacking species as compared to when it's a small molecule ion like fluoride, where the nucleus strongly attracts the outermost shell electrons and they are not therefore available for bonding with other electron lacking species. So that trend is also these other ions also follow the same trend, and also these other molecules. Then we will also discuss solvent effects on nucleophilicity. So here we will start with a solvent which are in the class known as protic solvents. So another factor in the nucleophilicity of these ions is their solvation, particularly in protic solvents. And what are protic solvents? A protic solvent is one that has acidic protons, usually in the form of OH or NH. When hydrogen is attached to a very highly electronegative atom like oxygen, or when it's attached to nitrogen, you find that the hydrogen will be acidic, meaning it will have either partial positive charge or complete positive charge. So in the case of being bonded to oxygen or nitrogen, it will have some partial positive charge, so it becomes acidic, and also in the case of NH. So when you have a solvent molecule which has OH or NH, then it will lead to acidic hydrogens or protons, which will easily form hydrogen bonds with the nucleophile, which is negatively charged. So these groups form hydrogen bonds to negatively charged nucleophiles. Protic solvents, especially alcohols, are convenient solvents for nucleophilic substitution because the reagents, alkyl halides, and nucleophiles tend to be quite soluble. If you remember in your first year, there's an experiment you did which the principle was that like dissolves like. So if you have a non-polar solvent, it will dissolve non-polar reagents, and if you have a polar solvent, it will dissolve polar reagents. And in this case, an alcohol is polar, and it will dissolve easily alkyl halides which are polar, and also nucleophiles which are polar. So they tend to be very good solvents for these particular reagents or reactants, alkyl halides, which is a substrate in SN2 reaction, and also nucleophiles. Most of the time, they are negatively charged. Even if you have a neutral nucleophile, it will also be polarized in most cases. So these protic solvents are very good, convenient for dissolving these reagents in SN1 reactions. But the problem is that they also drag the nucleophile from attacking the electrophile from the backside because they form hydrogen bonds. So small ions are solvated much more strongly than large anions in a protic solvent because the solvent approaches a small anion more closely and forms stronger hydrogen bonds. So there is always the formation of hydrogen bonds with protic solvents between the nucleophile, which is negatively charged, and also the protic solvent. And we've said protic solvents are the ones which have OH and NH. So if they have OH, in this case, you have this OH, and therefore this hydrogen will have some partial positive charge because it's attached to oxygen, which is more electronegative. So because of that partial positive charge, it will be attracted to this negative charge on fluoride, and not only fluoride, but any nucleophile, which most of the time is negatively charged. But even if it's neutral, it's usually polar, so it can still form hydrogen bonds with those other neutral nucleophiles. But SN2 reactions require strong nucleophiles. Most of the time, strong nucleophiles are negatively charged. So these hydrogen bonds here, which will be formed, and of course, the smaller the anion, the larger the number of hydrogen bonds. And when it's larger, the smaller the number of hydrogen bonds to the solvent. So this is a very small ion, an ion, so it's going to attract a lot of hydrogen bonds or water molecules. That process is known as solvation. When it's forming hydrogen bonds to the anion, it's being solvated by the solvent molecules. So it will attract a larger number as compared to the larger ions or anions like iodide ions. So for this nucleophile to form a new bond, to donate its electrons to form a new bond with this electrophilic carbon, it means this has to get out of the way. These solvent molecules have to be stripped by breaking these hydrogen bonds, and that will require higher energy or it will require an energy to break those hydrogen bonds off. And because of that, we find that fluoride ions, as much as it's negatively charged, it becomes a poor nucleophile because of the fact that it forms, it's solvated by these protic solvents. So protic solvents and always make the fluoride or any nucleophile to be a poor nucleophile, especially the smaller ones, which are most of the time solvated more as compared to the larger ones. So when an anion reacts as a nucleophile, energy is required to strip off some of the molecules, of course the solvent molecules, breaking some of the hydrogen bonds that stabilize the solvated anion. Of course, by them forming hydrogen bonds, this because it has some partial positive charge, it tries to stabilize the negative charge. Stabilize meaning trying to reduce that negative charge. More energy is required to strip off solvent from a small, strongly solvated anion, such as fluoride ion, than a larger, diffuse, less strongly solvated ion like iodide. The enhanced solvation of a small anion in protic solvents requiring more energy to strip off their solvent molecules reduce their nucleophilicity. So that's how the fluoride ions or anions become, the nucleophilicity is reduced because of the fact that they get solvated with the solvent molecules in protic solvents. This trend reinforces the trend in polarizability. The polarizability increases with increasing atomic number, and the solvation energy in protic solvent decreases in increasing atomic number. So we've said for the larger ions like iodide, they usually don't get too much solvated. So the energy which will be used to strip off the solvent or protic solvent molecules will be less as compared to when it's small. So that's why the solvation energy decreases in increasing atomic number. Therefore, nucleophilicity in protic solvents increases down a column in the periodic table as long as we compare similar species with similar charges. So nucleophilicity increases in protic solvents. It increases down the periodic table, down the column in the periodic table in protic solvents. So we will stop there. Next time we will discuss on how protic solvents also affect nucleophilicity or in SN2 reactions. Thank you.